Hello, everyone. I'm excited today to tell you about my research regarding PET-degrading enzymes and their production in the bacterium E. coli. First of all, I want to give you a short introduction, because single-use items like this PET bottle are usually recycled with thermomechanical means a number of times, but after that, they usually end up incinerated, which produces a lot of CO2, or they are landfilled. This is also not great, of course, because it stays there a long time. This will be me in 200 years. I will not be there anymore, but my PET bottle, my PET waste, it will still be there. So what can we do? One answer to this would be enzymatic recycling. And enzymatic recycling works in a way where the enzyme cleaves the bonds in between the PET polymer and produces monomers, terephthalic acid and ethylene glycol, which can then be in turn used to produce more PET bottles. And this can be done indefinitely. So it's actually circular PET economy, which is great. The challenges here are that we usually see slow enzymatic conversion rates with enzymatic recycling at room temperature, like 30 degrees, it takes a few months. So elevated temperatures are advised, and the enzymes are hard to produce. So our project partners in Leipzig set out to find an enzyme that can withstand high temperatures, and they found it in a compost inside a cemetery in Leipzig, actually. So this enzyme candidate is called PHL7, and it can withstand very high temperatures. We want to degrade our PET at 70 degrees, so it has to be thermostable. And it should be fast, and it is. It only takes like 24 hours to degrade our PET waste, and it is very stable. So you can freeze it, you can dry it, you can store it prolonged, so that is great too. And with that, we set out to see if it works. And this was a sample we did in our lab. First, we have our PET sample, and in the course of a day, is actually gone. So pretty impressive, I would say. But we still need to produce so much that we can actually make a difference. So our goal was to set up a process where we can actually produce enough enzyme. And here are reactors, and we wanted to produce active enzyme. We wanted to produce a lot, and we wanted to have it inside of the, outside of the cell, not inside, because breaking open the cells and purifying is costly. So our first process did not work so well. 5 is the negative control, and 6 is where our enzyme should be. The arrow should indicate a broadband, but we see nothing. So did not work well. And we kind of expected that, so we needed to do some adaptation. And first we did codon optimization, where we just took the DNA and adapted it for the use in E. coli. Next, we cloned some variants to see which one would work best. And we took a strain, an E. coli strain, that was adapted to produce a lot of enzyme. So we should have more and higher titers. And with all of that, we first selected in a small scale. So that was a plate with just under 1 milliliter, and looked if we found a variant that could actually be helpful. And with the best one, we went into the larger scale. So this is a set of 4 vessels with each 1 liter about. And here we wanted to see the production conditions. Can we find a setting that would actually give us a suspension where we have highly active enzyme? And as you can see in the graph, there were some conditions that were able to completely degrade PET, and others were not so great. So that was nice to see. And with the variation of induction strength, pH, temperature, and feed rate, we combined to find an ideal process. But not only we were busy, all our project partners in Leipzig were busy too, because they actually went on to modify the enzyme to make it even more capable, to make it better. And they did. They found an enzyme that then could actually work at 73 degrees, which also made it more stable and faster. So that can degrade PET in only 16 hours. And we took all of that together the process, the better enzyme, all of it. And this is how we started, and this is how we are now. So you see the broad band, this is already diluted 1 to 15. So we're pretty satisfied with our work, because at one stage I was like, we will never do this, but we did. And we're pretty happy about this. But where is the enzyme now? When you took the reactors and we took a sample and centrifuged it, at the bottom you see the bacterial cells, and on the top is a liquid with the enzyme. And you don't need to do anything further. You don't need to crack open the cells. You don't need to purify. You can take it as is, dilute it, and then degrade the PET. So the blue line here is the purified enzyme. And we wanted to come as close to this as possible. And the green lines are some of our attempts. And the dark green line here is how close we actually were to getting the performance of the purified enzyme without any costly purification, so pretty close. And with a setup with the 4 × 1 liter reactors, we would be able to degrade 1,000 half-liter bottles of PET. So this is really, really cool, I would say. Was a great PhD thesis, but still we want to do more. We need more enzyme. How could we do this? Continuous enzyme production. Here we have a feed, a constant feed going into the first reactor, feeding the cells in the second where they get induced, and here the enzyme is produced, and we have constant enzyme output to really satisfy our need of the enzyme. And with that, I want to thank my team and my supervisors who supported me throughout this thesis, because doing a PhD is not always easy. You have to be resilient, and yeah, without them, I don't think it would have been the fun time it was. Thank you.